Hi guys, welcome to our CAD programming lessons, and for today let's talk about CAD assemblies and related stuff like how to represent CAD assemblies in OpenCascade and how to visualize them in a 3D scene. Let's start with the concept, and for that let's take somewhat to example which would be illustrative enough. Let's speak about something which is a car chassis, and car chassis is essentially composed of wheel, then axle, which is a somewhat cylindrical bar connecting two wheels together, and we have another component like this. We have another axle with two wheels here, and now we want to represent this whole thing using some data structure in OpenCascade, and it's not going to be anymore like one solid object here, because what we really need to have these 6 components. And the essential thing about it, the essential property of such a complex product is to have unique geometry defined only once, and we can basically start from listing what is called like a simplified bill of material. And in the simplified form, it's going to be just a plain list of parts and components with the numbers of the occurrences in my assembly. So I'm going to have a wheel, which is a solid object, and I have an axle. This is this cylindrical bar connecting two wheels together, and these two entities, these two guides, are defined in their local coordinate referentials. Like I have some local coordinate system associated with them, and also for my axle it's going to be like a different coordinate system which is somehow baked into this geometric representation here. So having these two entities in my bill of material, I can try to compose a scene, I can try to compose an assembly. And these entities here, I would call them like originals or prototypes. In my scene, I have somewhere this global coordinate system like X, Y, and Z. And I want to put these prototypes, I want to put them into my scene with different transformation, because if I just use this local transformation associated with my CAD definition, then I'm going to have them here in the global original, which is basically not what I want to have there, right? So to compose an assembly, I start with a somewhat root node, which is going to be just a container with a sort of a name. So here I would call it like a chassis. And it's not going to contain any geometry by itself. It will rather contain a couple of references or components, like this component here, and then this component here. It's up to me to decide how would I compose my scene, because I might want to just insert these 4 wheels right into my scene, you know, having these 4 wheels like that, like wheel number 1, wheel number 2, wheel number 3, but I want to give it a more structured representation, and that's why I would propose and I would prefer to have these 2 subassemblies here. And that's why in my bill of material I'm also going to add this component. Like I will have also wheel, axle, and this wheel axle is going to be a subassembly that contains 2 wheels and 1 axle, like this cylindrical bar in here. So let's call it like wheel, axle, I don't know, 1, and this is going to be wheel, axle 2. So here I am going to use these components. These are essentially the references to wheel, axle prototype, to this subassembly here. So they both use the same definition of this subassembly, which is wheel axle. There we go. And this wheel axle in its turn, it's a composition of 2 wheels connected to this road here. So this is going to be like wheel maybe left, and this is wheel right. So I have 2 references here. I want them to point to the same geometric definition, to the same wheel from my bill of material. So that's why I also have this couple of links here pointing to my wheel, to my prototype. So this is a prototype. This is another prototype from my bill of material, and I also have this axle here, which I need to have in my wheel axle subassembly. So let's put it here. I'm also going to give it some reference, which is going to be like axle, I don't know, ref. Because I need to take my axle from its local coordinate system and give it some placement in their wheel axle subassembly here. So it's going to point to this axle from my bill of material. And that's going to be another prototype. There we go. So basically, if you look at this hierarchy here, what is called a hierarchical assembly graph, when I have different types of entities here, and one of them is a root entity, it's very common to have just one root, but it's not necessary. You can also have like different roots, many roots in your assembly. So we have this root entity, which is a pure organizational entity. And then we have what we call references. So I will put those guys in blue, like this is a reference. It's not real geometry, it's a reference to my geometry, which takes this wheel axle prototype from my bill of material and puts it to the modeling scene with some transformation like T1. So I take my wheel axle and I somehow move and rotate it to find a good placement of this wheel axle subassembly in my modeling scene. And wheel axle 2 is going to have different transformation because I need to shift it like somehow to shift it to the back, and this is going to be T2. Then I have 3 more references. I have wheel on the left and wheel on the right. So these are 2 more references with their associated transformations, which have some sense with respect to this wheel axle subassembly here. So it's going to have transformation like T3 and T4. So T3 like takes this wheel from its local coordinate system and puts it here. And then I need to shift or maybe even mirror this wheel to put it to the right. So this is going to be T4. And the final reference here is the axle reference, because I still have to take this cylindrical bar from my bill of material and put it between these 2 wheels. So this graph here is what we call Hierarchical Assembly Graph, or HAG. And we can draw this hierarchical assembly graph in a more simplified way if we say, okay, we have a chassis, and then chassis is composed of wheel axle, and we are going to have 2 wheel axle subassemblies. So I put like 2 links here. Instance number 1 and instance number 2. And each wheel axle contains 2 wheels. So I have 2 links, 2 instances of my wheel in my wheel axle component, in my wheel axle subassembly, and I have 1 reference to the axle bar here. So this is a kind of, equivalent form, equivalent drawing for this hierarchical assembly graph, but it doesn't expose, it doesn't contain any references explicitly. Instead of drawing these nodes here as reference node, I just put these links. And this is something you can find in literature explaining how CAD systems are designed, how would you design your assemblies and stuff. Then let's see how would we address a single entity in our scene, because we have this scene graph or assembly graph, and let's say I want to address this wheel here. And that is something really important when we speak about hierarchical assembly graphs. We need to understand that in order to address this left wheel in the wheel axle 1, what we need to do, we need to traverse this graph. We need to go to wheel axle 1 first. I'm going to use this link here in order to reach my left wheel and finally my wheel. So this is a path which addresses my left wheel in this component here. And if I want to take the right wheel, I'm still going to go the same link here for wheel axle 1 and go here, but now I need to go to the right wheel here. So it's important to understand that in order to address a single entity in your scene, you need to address it by the path in your hierarchical assembly graph. Not by a node in the graph, but by a path in the graph. So this is how we basically design assemblies, and this is a structure which you would normally have in a step file, and then you can read using OpenCascade. You can read it to somewhat called XDE, which is Extended Data Exchange Framework. And in XDE, which is based on OCAF, this is going to be a label for a root node, a label for a reference node, which is inserted as a component to my root label. And then I will have like a reference here to another label. So each node in my graph is going to be represented by an OCAF label. Now, if you want to learn more about how assemblies are represented in these hierarchical assembly graphs, you may want also to read our paper on the subject. And here we explain quite a bit what is a hierarchical assembly graph and how you are supposed to work with it, and what are the issues which you normally going to face when you work with this sort of a data structure. And here we have this example with chassis, wheel axle, wheel, and stuff. Also, if you are curious about XDE and how you are supposed to work with the XDE data framework, then I invite you also to get into web page from analysissitus.org. You go here, you go to the features, you find this assembly section in here, and there is an introduction to XDE and the API which you might want to call when you work with a CAD assembly from C++ or from a batch process. So this is a kind of an explanation which dives into more detail about the subject. Now let's have a bit of practice with all that, and if you go to our website with our lessons, with our exercises, you will find out there this lesson 12 XDE, and there, if you go inside, you will find this data folder with chassis step file, and this is a step file which I want to use as a demonstration. So I'm going to use Analysis Situs for that. You can also use draw actually, but let me use this thing here. So I'm going to call this awesome XDE set of commands to work with an XDE document, and I'm going to show you how it all looks when you load it into the memory, and how it feels and what can you get from there. So awesome XDE load, this is something to load my step file into a document. I'm going to give a model a name m, and then I need to pass like a file name here, and this is going to be this file. Yeah, and now we have this document. We can ask what is m. M is XDE document. So now what I can do, I can browse this XDE document using awesome XDE, then browse, and give it a model name. So there we go. We have a root entity here. So let me also put this picture so that we can match what do we see from the real model from with what we expect to have. Like we have this assembly graph drawing, and then we have like a real thing here in the browser. So we have a root entity, a root node, which is a kind of artificial thing, because the real assembly starts from this chassis in here, and then we have like two references. You see these names on the left column, and you also see the persistent ID, the entry of the corresponding OCAF label. This is what I was talking about. So here we have like two references, wheel axle 1 and wheel axle 2. And if we go inside this wheel axle, we will see that actually we have this prototype entity, which is a wheel axle, and it's exactly the same prototype for the second reference, for the second wheel axle here. It's 113 label in OCAF. And if I expand on this entity, I see that I have like 3 references. And I have wheel 1, which is probably the left wheel, and wheel 2. And then I have axle. And you see that exactly the same labels, exactly the same references are reused in this second branch for my wheel axle, because it is exactly the same prototype. The same prototype which comes from this bill of material, and this entity in my bill of material, it has exactly the same structure. Whenever I put it to this references or to this reference, it doesn't matter. So if I expand on a wheel, I see what's a real CAD part, wheel, and wheel number 2, it's exactly the same CAD part. And this way I kind of have the same object, the same solid object, referenced like twice from one component, which is VLAXL, and if I count all the occurrences, I will find out that there are like 4 occurrences of the single label 114 with different transformations. And as we discussed, the ultimate transformation of this entity would be the composition of the transformations defined by all the references in my hierarchical assembly graph. So I can visualize it using VTK visualization framework. So this is my assembly graph, and you see that it's something which looks like car chassis. Yeah. Okay. All right. So let's see how could we do the same thing using bare C++ programming. So here I invite you just to clone the repository of the 12th lesson, and we are not going to program a lot for today. We will just discover, we will just see what is inside, what do we have in this lesson, because this lesson is basically something you might want to copy and paste into your project and then do some modifications to better, tailor it to your needs. So here in the project tree, what do we have? We have a viewer and viewer interactor. These are the 2 entities which we've discussed in the lesson related to AIS visualization frameworks. So let's not waste time on revisiting those things. And instead, let's just have a look on this main function. So this is a main function where we create this instance of our viewer. And then what do we expect is we expect to have one argument which will point to our CAD object which we want to visualize. So let me take this file name from here, and I'm going to run this main function, passing there the argument. I go to debugging, I have here command arguments. Let me also switch to debug mode. Yeah, and here I will put this path to my chassis dot step. So here we are, we see that the viewer is kind of initialized. We have this window here, and then since we have an argument, what we do, we read a step file into an OCAF document, and for that there is this read step with meta function. If we step inside this function, we see that instead of using step control reader, which is a pure step reader provided with OpenCascade, we use something called step CAF control reader, which is a sort of a bridge that is capable of reading not only geometric information but also all sorts of metadata from a step file, like assembly hierarchy, colors, names, layers, and whatnot. So here, as we saw in the previous lessons related to OCAF, we need to create an application. Then we define a format. This time it's not bin OCAF, it's a bin XCAF, because we are going to use another embedded format from OpenCascade, which is dedicated to XDE documents. So here we define this format, we create a new document, and then we read a file. We check that the status of the reader is done. If not, we have to close our document and return null pointer. And then we run this transfer, because step reading is a 2-phase process. We first read the file, and then we transfer all the data from in-memory representation of a file to real data structures of OpenCascade, ranging from parametric curves and surfaces to OCAF structure for assemblies. So there we go, we transfer it and we return the document. So we are done here, the document is not null, it's a real OCAF document. And then we use another thing, another class from this exercise, which is display scene. And we are going to see what is inside this display scene a bit later. So for now, let's just execute what do we have and give it a go and see what we are going to have here. Finally, we have this assembly here visualized in AIS viewer, and you see that selection by default works at a part level, so we can select each individual occurrence of our part in a scene. So there we go, and now let's see what is this display scene all about. So here, if you go to the header file, you see that it's a typical class. It inherits from standard transient in order to take advantage of smart pointers mechanism of OpenCascade, but it's not really important, and you can keep it just as a pure class without any inheritance in there. So what do we have here? We initialize our display scene object with tdoc std document, which is our OCAF document, and then we also give it like an interactive context. And if you remember from one of the previous lessons, we discussed that this interactive context thingy is a kind of visualization facade which provides you with access to all the visualization functionality coming from AIS package. So here the idea is to simply initialize a couple of fields in our class, and then the real job is done in this execute function. So let's see what's going to happen in there, and let's put a breakpoint to this execute function, and I will give it another try. So let me run this whole thing again. And okay, now we are in this execute function. We check that this document is not null, and the first thing we do, we kind of erase everything from our scene, we clean up our viewer, and then we start working with OCAF document, which is a bit involved thing actually, because it's not pretty obvious how would you work with XDE documents, and a few folks asked on our forum how am I supposed to work with all those colors and hierarchy, and the honest answer would be just you have to copy and paste a bit of code which works. So this is this kind of code, and I invite you to just use it as a bare minimum to start from when you work with XDE documents and visualization. So here the idea is that having this OCAF document, we start iterating our labels in a way to create all the interactive objects as long as we visit our labels, as long as we understand what each particular label means, if it is a root label or if it's a reference label, when we need to take the transformation which is associated with this label, or if it's a prototype, when we have to create the real actor on a scene, the real graphical data structure which would carry on all the geometries and facets. But before we dive deeper into this logic here, let me also show you how it really looks in OCAF, because this scene tree is, is not something which you have in memory really, because this is something you might want to expose to your users when you develop your own application. But when you work with OCAF, when you work with an XDE document at low level, you do not have this scene tree. You rather have something different, and for that we can call something which is awesome XDE df browse and give it a model name. So here we go. We have this document, which is an OCAF document. And what do we have here? We have different sections. And the first section is shapes. And this is where you will expect to find this assembly hierarchy. Then we have these colors. Then we have layers, dimensions and geometric tolerances, materials, views, clipping planes, nodes. So these things, starting from layers down to nodes, I think we do not care about them that much, because what we really have to have is this shapes hierarchy representing the assembly hierarchy and essentially the hierarchical assembly graph, and also the colors associated with our parts, and actually the colors can also be associated with the boundary elements like faces, edges, and even vertices of our part. So here in the shapes we have a root. Let's put it to the right, and let's see what's going to happen if we continue debugging. So we have this structure over here, and we have a real code on the left. So we take all the free shapes. It means that we take all the roots of our model, and here I would expect to have just one entity. So yeah, it's a list of one element. This is what we have, and then we start iterating over the root labels, and we take the first label, and you see it's it's a label with a tag 1, and if you go to its father, it's also 1 and 0. So it's a 1, 1, 1 and 0. This is this label. Then we take this label and we call this display item method on it, and then the first thing we do, we check if it's a reference or not. And actually in OCAF, if you have this U attribute with this ID, it means that this is an assembly. It's basically just a flag saying that this label is an assembly label. So it's not reference here, and this is why this is reference returns false. And then we take an entry. You see it's this 1110, and what we essentially do, we try to compose this path which we are going to use to address a unique scene object on our scene. So what do we have then? We were checking right above that it's an assembly, and if it's not an assembly, then it's probably right time to create some graphical structure, but it was an assembly, and that's why this is assembly method returned true. And when we get here, so we do some, yeah. And finally, in the case of an assembly, what we have to do, we have to iterate over the children of this label. And here we have this chassis. And you see it's always kind of two-level hierarchy in the XDE document, because we are not going to have nested hierarchy down to the whole depth of assembly graph. Instead, we have this component which is sort of a reference to the prototype. You see this component, it references 2110, and this is this entity here. This is this label, which is actually a prototype for our chassis. So we take this child label and we recursively continue expanding our tree. So we call again this display item method, we get the label. This time it's a reference, because this label here is a reference. We can see it by checking this attribute, which is tdata std3 node. So this time it's a reference. And if it's a reference, then what I have to do, I have to jump from this label, from here to this label. So I need to get back to the first level hierarchy in my shapes folder, in my shapes group, and get to this label instead. And this is what's happening here. I get this ref label, and you see it's going to have tag 2, and its father is 1, and then 1, and then 0. So it's this label finally. So we take its entry, it's an entry of the original label, we compose like a path. It's still an assembly, it's still not the prototype which we are going to visualize directly, and that's why we continue, and we want to iterate over its children. This time this chassis is going to contain two references, like wheel axle 1 and wheel axle 2. So this is going to be these two guys here, wheel axle 1 and wheel axle 2. Actually, the very idea is that we take a shape which is a solid from our part, which is a property as T-solid, and then we create finally this AIS object. This is a presentation object for our wheel. So we create this colored shape object, but here we are not going to have as many presentations, as many wheels we have in our assembly, because what we really want to have is we want to have just one object, like an object from our bill of material. This is going to be our AIS object. And then we want to create more lightweight objects which would reference this prototype object, which would reference this AIS colored shape object, and they will serve as occurrences of this object in our scene with different transformation. And this is where AIS comes with what is called a connected interactive framework. And this is how we do this. We create one colored shape for our prototype object, for our part, and then we create a connected interactive like a reference to this object and connect this lightweight presentation object to our original object. So this is pretty important thing which we discussed, and it has its own implications, like what will happen, because you see that I have only two prototypes in my hierarchical assembly graph for my solid object. So if I go and open this file, this chassis, like if I open it here, then whatever I do with one of the instances of this object, if I kind of modify this wheel here, what's going to happen is that all the instances of this exact object will also get the same modification. So I modify one object and all the objects are kind of modified synchronously, because essentially these are just the same objects with different transformation. This is what I mean to highlight here. So here on Fusion I can test it out. I can also see, I can also see this assembly structure in there, like I have a chassis, I have Vilaxel, and I have all those things. Because, this hierarchy, this structure of my assembly, it really comes from a step standard. It's not something specific to OpenCascade, it's how people design assemblies. So it's a general principle, and if you use like visualization front end wisely, if you do not waste your memory, if you do not create the same object as many times, as many occurrences you have for it in your scene, then you are going to get to efficient solution, you're going to have efficient scene. One other thing which is related to this whole visualization business is that it's this architecture of connected interactives, and actually this XDE plus colored shape architecture is suitable not only for assemblies, it's also suitable for single parts when you want to have, colorized shapes. If you want to read a step file with all the metadata and have like a colored object in your scene, you can also benefit from exactly the same architecture. And for that, let me show you another example. So I can change this input for my application from an assembly to this single part object. And let's see what's going to happen, because actually there is no hierarchical assembly graph anymore in this model, but still there are some colors I want to visualize, there are some colors I want to have on my scene, and you see all those colors, they will kind of visualized nicely. So I have all my metadata in my viewer without spending much time on it, because really I reused as much as possible from OpenCascade, and here the only custom thing is actually the principle how would you iterate your hierarchical assembly graph, and how would you construct those colored shape objects and the corresponding connected interactives. But when it comes to colors and stuff, you only take what comes from OpenCascade. And here in this code we do not do anything related to coloring, and we do not try to compose our object to colorize each particular face, each specific face individually. Rather, when we create this OCAF PRS AIS object, we pass a label here, and then we let OpenCascade do what it does. Like OpenCascade is going to automatically extract all those styles for surfaces and curves and vertices, and generic colors of parts as well, and it will put all these colors into this AIS colored shape thingy. So one important property of this AIS colored shape is that whenever you have like a colored face, like imagine a box with a colored face, and you have like a red face on a on a green box, this red face is not going to be another object. It will be like a colored set of primitives on the initial mesh representing this box. And this is what this AIS colored shape does. So it creates this this data structure in a sort of integrated way. So you do not duplicate your graphical primitives in order to colorize something. You just reuse the same mesh. So that's pretty important for performance, if you think about it. Okay, so I think that's it for today. I think we covered everything related to the concept of assembly modeling in OpenCascade, and not only in OpenCascade actually, because it's kind of a standard thing. So I invite you to give it a try. I invite you to clone this repository and play with the code in here, and maybe try to customize it to your needs if you wish to go on with XDE framework for assembly representation and AIS for visualization, because you might also want to design your own data structures, and you're not obliged to use XDE or AIS. You can use whatever you want. You can use, for example, database engine, or you can design your own data model also based on OCAF, why not? So this is just, you know, a solution which is available out of the box, and you can benefit from what already exists in the kernel. So have fun with all this, and see you in an upcoming lesson.